In the previous video, we were discussing about the various types of cleavage of a covalent bond. So you have homolytic cleavage and heterolytic cleavage. And when a reaction takes place, there are substances which are formed in between before the formation of the product, and these are called as reaction intermediates. And there are basically three types of, they're technically like more than three, but we will be learning about three types of reaction intermediates, that is carbocations, carbanions, and free radicals. All of these vary with respect to how they have been formed and the charge they possess. So carbocations have a positive charge. So they have a carbon atom with a positive charge. And this is formed by heterolytic fission. So here, let's for example take a carbon molecule where X is supposed to be more electronegative than carbon. So this means the electrons of this covalent bond will go to X, and this will lead to the formation of a positively charged carbon, and this is called the carbocation, and then negatively charged X minus. Another example is CH3Br, bromomethane. So bromine is more electronegative than carbon. So this covalent bond will be shifted to, the electrons of the covalent bond will be shifted to bromine, and this will lead to the formation of a carbocation plus Br minus. So this carbocation actually has a positive charge, and the carbon has 6 electrons in it. So carbocations are basically classified into primary, secondary, and tertiary, and this is based on the number of carbon atoms the carbocation is bound to. When the carbon is not bound to any other carbon atoms, it is basically the methyl carbocation. When it is bound to one carbon, it is a primary. This is primary, this is secondary, and tertiary. Secondary has two carbon atoms bound to the carbocation, the carbon of the carbocation, whereas in case of tertiary, it is bound to 3 other carbon atoms. Now, methyl is a plus I group, which means if you remember, we had discussed about inductive effect, mesomeric, basically the electronic effects or the electron displacement effects in the previous set of videos. So we know that a CH3 group is a plus I group, and it is electron releasing in nature. So what happens is, because now if you compare here, you have only one CH3 group, right? Here you have two CH3 groups, and here you have 3 CH3 groups. All of this will, has an effect on the stability of the carbocation. In case of methyl, it does not have any electron releasing groups, and so it is not stabilized by the inductive effect. But in case of primary, there is a CH3 group, so the electrons are going to get displaced towards the carbocation, carbon, so this carbon, and this is going to help in its stability. Whereas when you have two CH3 groups, you have more stability towards the carbocation, because there are two groups which are electron releasing, and in this case there are 3. So more is the number of alkyl groups, more will be the degree of dispersal of the positive charge. So the positive charge is going to get dispersed, and more stable will be the carbocation. And because of that, a tertiary carbocation is more stable than secondary, which is more stable than primary, which is more stable than methyl. So again, I'll repeat, here we are talking about inductive effect. CH3 has a tendency to donate give electrons. It's an electron releasing group. So what happens is, this positive charge is going to get dispersed because of the presence of 3 CH3 groups in case of a tertiary, which is more stable because of the presence of a 3 methyl group, 3 CH3 groups, which are in turn going to stabilize it because of the inductive effect. The stability of the carbocation can also be explained with respect to hyperconjugation. Now I will just draw the hyperconjugation structures for tertiary. So in case of tertiary, you have the number of hydrogens which are present is 3 plus 3 plus 3. That's 9 alpha hydrogen atoms. So generally, so for hyperconjugation, we know it's basically no bond resonance. So here the number of hyperconjugation structure would be 9, and that's formed because this particular bond is going to get shifted here, and here you will have another hydrogen atom. And since it's a it's a tertiary carbocation, there are two CH3 groups. Oh, sorry. If you want to learn how to draw the hyperconjugation structures, do check out the video I did on the same. Now, in case of this, again, if you know, I mean, basically these two hydrogens will also take part, and you'll have 3 structures for each carbon. And since there are 3 carbons, you have 9 hyperconjugated structure in case of a tertiary carbocation. So here, in case of a tertiary carbocation, we have 9 hyperconjugative structures. Basically, the total number of hydrogen atoms which are present. Okay, and here in case of this and in case of a secondary, we have only 6 hyperconjugative structure. This hydrogen will not take part in the formation of the hyperconjugative structures. Whereas in case of primary, we just have 3. And in case of methyl, we have 0 hyperconjugative structures. So based on hyperconjugation as well, we can explain that tertiary is more stable than secondary, is more stable than primary, is more stable than methyl. So stability of the carbocation, first of all, inductive effect, we are talking about the presence of CH3 groups. These groups are making sure that the positive charge on the carbocation is getting dispersed. And because of that, more are the number of CH3 groups present, more will be the stability. In case of hyperconjugation, because of the number of more are the number of hyperconjugative structures, more is the stability. And so because of that, tertiary is having 9 hyperconjugative structures, secondary is just having 6, and primary is having 3, and methyl will not form any hyperconjugative structures. And that again explains the stability of the carbocation. Now, in case of a benzyl carbocation, the stability is because of resonance. So let's take the benzyl carbocation. So here you have a CH2 plus. Now, when we had already studied, about resonance. We know that the resonance structures are drawn by, and the arrows will show the movement of the electrons. So we will not move the positive charge, but we are moving the electrons, and that leads to the movement of the positive charge. So this moves towards the carbon, and so you have a carbon-carbon double bond. And to maintain its valency, the bond breaks, and so this moves. Then you have another structure, and so this bond is here, the positive charge is over here, double bond CH2, this bond moves downwards, and so you have a double bond here and a double bond here, CH2, double bond, positive charge, then this bond moves back to the benzene ring, and the carbon gets a positive charge. And this particular carbocation is resonance stabilized. So in case of our carbocations which are present with the benzyl benzyl carbocation, they are resonance stabilized. So we've learned about hyperconjugation, we've learned about inductive effect as well as the resonance effect. Now assuming, so if there were more, instead of CH2 there was another benzyl group attached to it, that would have been more stable. So because the number of resonance structures would be more, right? So C6H5 taken thrice C carbocation is more stable than C6H5. Again, this This technically 2, which means it's a secondary carbocation, which is more stable than, oh sorry, CH, which is more stable than C6H5 CH2. So more are the number of phenyl groups attached to the carbon, more will be the stability, because there will be more resonance structures, and that contributes to the stability. Again, it would be, I mean, if at this point you have not learned about inductive effect, mesomeric effect, hyperconjugation, and the electromeric effect, it would be better that you understand and learn that, and then come to the stability, or understanding the stability of various reaction intermediates. Now we've learned about the stability. Now we will be learning about the shape of the carbocation. So the shape of the carbocation is a trigonal, planar, and here this is its structure. It has one sp, basically an sp2 hybridized orbital or hybridization, and it has a bond angle of about 120 degrees. Now it forms 3 sigma bonds with other atoms, and it has a positive charge. So with that, we've complete carbocations. Carbocations are formed by the heterolytic fission between carbon and another atom, and the electrons move towards the other atom, leaving the carbon with a positive charge. The carbon has 6 electrons, and based on the number of carbon atoms the carbocation is attached to, you have primary, secondary, and tertiary. So in case of primary, you have only 1 carbon, and in case of secondary, 2, tertiary, 3. The stability of the carbocations can be explained using hyperconjugation as well as inductive effects, and in case of a benzyl carbocation, we can explain it using resonance. It is a trigonal planar shape with an angle of 120 degrees, and it is sp2 hybridized. In the next video, we will be discussing about carbanion. Do check it out.